Hello everyone, this is the part 2 video of concept of maxima and minima. Some concepts are discussed in the part 1 video. Now let us discuss the remaining concepts. First, what is concave upward and concave downward? If the graph of f lies above all of its tangents on an interval, then it is called concave upward on I. If the graph of f lies below all of its tangents on I, it is called concave downward on I. Now I explain what is concave upward curve and what is concave downward curve through these diagrams. The first two diagrams, this is the first diagram, this is second diagram. The first two diagrams shows the graph of two increasing functions on a comma b. Both graphs join the point A to the point B. Both graphs join the point A to the point B. But they look different. This is this type, this is this type. Because they bend in different directions. How can we distinguish between these two types of behavior? In the next two diagrams, third and fourth diagram. In the next two diagrams, tangent to these curves have been drawn at several points. In the diagram 3, the curve lies above the tangents and f is called concave upward on a comma b by using this definition. Okay. In the diagram, third diagram, the curve lies above the tangents. The curve lies above the tangents. So f is called concave upward. Concave upward. In the diagram 4, the curve lies below the tangents. So that graph G is called, this G is called concave downward on A comma B. This is concave downward by using that definition. The definition says if the graph of f lies above all of its tangents on an interval, then it is called concave upward. This is that type. This is concave upward. And if the graph of f lies below all of its tangents, so this is concave downward curve. This is the explanation of concave upward curve and concave downward curve. Now, concavity test. What is concavity test? If double dash of x greater than 0 for all x in I, then the graph of f is concave upward. This is the condition. F double dash of x greater than 0 for all x, then the graph of f is concave upward on interval I. F dash of x is less than 0 for all x in I, then the graph of f is concave downward on that interval I. This is the concavity test. Next, I explain what is inflection point. Inflection point. A point P on a curve y equal to f of x is called an inflection point if f is continuous there and the curve changes from concave upward to concave downward or from concave downward to concave upward at P. Okay. The curve changes from concave upward to downward or from concave downward to upward. Then the point is called the inflection points. And it is also continuous. F is continuous there. Okay, that interval F is continuous. It is the must condition. This is the definition of inflection point. Next, what is second derivative test? Suppose f double dash is continuous near C. If f dash of C equal to 0 and f double dash of C greater than 0, then f has a local minimum at C. Second is if f dash of C equal to 0 and f double dash of C less than 0, then f has a local maximum at C. This is the condition. Greater than 0, then f is local minimum. F has some local minimum at C, and f double dash of C less than 0, then f has a local maximum at C. This is the second derivative test. Next, I will give one example. That example gives how to check the curve is concave upward and concave downward in what interval and what is point of how to find the point of inflection and how to find the local maxima and minima by using second derivative test. I explained all these things, these three things in one example. Okay, first the curve is f of x equal to x power 4 minus 4x cube. So first I find the critical points. F dash of x equal to 4x cube minus 12x square. I solve the equation f dash of x equal to 0. This gives 4x, and 4x square is common. So x minus 3. So this is equal to 0. Points are x equal to 0 and x equal to 3. X equal to 0 and 3 are the critical points. Next, I find the second derivative, because here I check the second derivative test also. I find the local maxima and minima by using second derivative test. So I find the second derivative. This is 12x square minus 24x. To use the second derivative test, we evaluate f double dash at these critical number. Okay. First, f double dash of 0, that is 0. F double dash of 3, this is 36. This is greater than 0. Since f dash of 3 equal to 0 and f double dash of 3 equal to 36, this is greater than 0. So f of 3, this gives f of 3 equal to, what is the value of f of 3? Substitute 3 in the function f. I got minus 27 is a local minimum, because this is greater than 0. F double dash of c greater than 0. This is the second derivative test. Then f has a local minimum. So here f double dash of 3 greater than 0. So f of 3 is a local minimum value. That value is the minus 27. And another one case is available. F double dash of 0 equal to 0. Since f double dash of 0 equal to 0, the second derivative test gives no information about the critical number 0. But here I use the first derivative test. Since f dash of x less than 0 for x less than 0, and also for 0 less than x less than 3, 0 less than x less than 3. So the first derivative test tells us that f does not have a local maximum or local minimum at 0. F does not have a local maximum nor local minimum at 0 by using first derivative test. Okay. Next I explain in what interval that function, the graph is concave upward and concave downward. Okay. Since f double dash of x equal to 0, when x equal to 0 and f dash of x equal to 0. F double dash of x equal to 0, when x equal to 0 and x equal to 2. So equating f double dash of x equal to 0, I got the point x equal to 0 and 2. We divide the real line into intervals with these numbers, x equal to 0 and 2. How I got these numbers? I solve the equation f double dash of x equal to 0. So we divide the real line into these intervals, these numbers with these numbers as endpoints. So the interval is minus infinity to 0, 0 to 2 and 2 comma infinity. This is the interval. These three are interval. Now I check the f double dash of x is greater than 0 or less than 0. In the interval minus infinity comma 0, f double dash of x is always positive. Always positive. So this is concavity is upward, concave upward. And the interval 0 comma 2, the f double dash of x is always negative. Always negative. Substitute that value 0 comma 2 values in this function f double dash of x. I got the negative. So this is concave downward. Next 2 comma infinity interval, I got the sign plus, so it is concave upward. And here the point 0 comma 0 is an inflection point, because the curve changes from positive to negative. That means concave upward to concave downward. Okay, so 0 comma 0 is an inflection point. Next, similarly 2 comma minus 16, 2 is also one point in ix value. Okay, 2 comma minus 16, because f of 2 is minus 16. So 2 comma minus 16 is an inflection point because the curve changes from concave downward to concave upward. So here 0 comma 0 and 2 comma minus 16 is an inflection points. This is the one example of how to find the inflection point and how to check the curve is concave upward, downward, and how to find the local maxima and minima by using second derivative test. Next, maximum and minimum of values of two variable function. The next definition says what is local maximum and local minimum in two variable function. A function of two variables has a local maximum at a comma b if f of x comma y less than or equal to f of a comma b when x comma y is near a comma b only. So it is called local maximum. That means that f of x comma y less than or equal to f of a comma b for all points x comma y in some disk with the center a comma b. Then the number f of a comma b is called a local maximum value. If f of x comma y greater than or equal to f of a comma b when x comma y is near a comma b, then f has a local minimum at a comma b and f of a comma b is a local minimum value. This is the definition of local maximum and local minimum of two variable function. Suppose if the inequality in definition, that is f of x comma y less than or equal to f of a comma b and f of x comma y greater than or equal to f of a comma b, these two inequalities hold for all points x comma y in the domain of f, then f has an absolute maximum and f has an absolute minimum at a comma b. This is the only difference of local maximum and absolute maximum. Here x comma y is near a comma b, but in the absolute maximum f of x comma y greater less than or equal to f of a comma b at all points of x comma y in the domain of f, then it is called the absolute maximum value. F of a comma b is called a absolute maximum value. Similarly, f of a comma b is called a absolute minimum value. Suppose the inequality is f of x comma y greater than or equal to f of a comma b, then it is absolute minimum. Next, one theorem, if f has a local maximum or minimum at a comma b and the first order partial derivatives of f exists there fx of a comma b equal to 0, then fx equal to 0 and fy equal to 0 at a comma b. This is the one theorem. Now I explain what is second derivatives test. Suppose the second partial derivatives of f are continuous on a disk with the center a comma b, and suppose that fx of a comma b equal to 0 and fy of a comma b equal to 0, that is a comma b is a critical point of f. Let you have to find the value of capital D, D of a comma b equal to fxx into fyy minus fxy whole square at the point a comma b. The first condition A is if D greater than 0 and fxx of a comma b also greater than 0, then f of a comma b is a local minimum. And second condition is if D greater than 0 and fxx of a comma b less than 0, then f of a comma b is a local maximum. Suppose if you got D less than 0, then f of a comma b is not a local maximum or minimum. This is the second derivative test. Next, I will give an example of second derivative test. Find the local maximum and minimum values and saddle points of one function is given. Okay, we first locate the critical points. So I first find the first derivative fx equal to 4x cube minus, this is 0, here 4y. This is fx. Fy equal to first derivative with respect to y, that is 4y minus 4y cube, 4y cube minus 4x. Setting these partial derivatives equal to 0, we obtain the equations, that is x cube. First is take it 4 outside, so I got x cube minus y equal to 0, and here y cube minus x equal to 0. To solve these equations, we substitute y equal to x cube from the first equation. From the first equation, I got y equal to x cube. I substitute the value of y equal to x cube in the second equation. This gives, this is 1, this is 2, this is 1 gives, so 2 gives y cube, that is x cube. X cube power cube is x power 9 minus x equal to 0. That is x power 9 minus x is x power 8 minus 1 equal to 0. That is x power 4 plus 1 x power 4 minus 1 equal to 0. Next, x into x power 4 plus 1 x square minus 1 x square plus 1 equal to 0. So these three are real roots, that is x equal to 0, 1 and minus 1, 0, 1 and minus 1. So the three critical points are here, that is substitute 0 in first this equation. I got 0 comma 0, these are the critical points, 1, 1 comma 1 and 1 comma minus 1 comma minus 1. These three are critical points. Next we calculate second partial derivatives, that is f x x. F x x is 12 x square, this is the f x x. Next f y y, that is 12 y square. F x y, that is 4, minus 4, sorry, minus 4. Okay, next I find the d value, that is first d of x comma y. That is formula says fxx fyy minus fxy whole square. This is the formula of d. So finally I got fxx into fy. That is 12 into 12, 144 x square into y square minus 16. This is the d of x comma y. First I substitute the critical point 0 comma 0. I got that value is minus 16. This is less than 0. So by less than 0, so the case C says, it follows from case C of the second derivative test that the origin is a saddle point. That means f has no local maximum or minimum at 0 comma 0. F has no local maximum or minimum at 0 comma 0. Okay, no local maximum or local minimum at 0 comma 0. So 0 comma 0 is called saddle point. Similarly, d of 1 comma 1, substitute 1 comma 1 in the d function. I got d of 1 comma 1 is 128. This is greater than 0. Greater than 0, then I have to check the next condition, fxx of a comma b. So fx x of 1 comma 1 equal to 12. This is also greater than 0. So the case A greater than 0, then f of 1 comma 1 equal to, that is f of 1 comma 1 equal to minus 1 is a local minimum value of that function. Next, similarly, d of minus 1 comma 1, here I write d of minus 1 comma minus 1 equal to 128. This is greater than 0. fxx of 1 minus 1 comma minus 1, this is equal to 12. This is also 12, greater than 0. So f of minus 1 also minus 1, it is also local minimum value. This is the one example of how to find the local maximum and minimum values by using of two variable function by using second derivative test. Next, method of Lagrange multipliers. Okay, next I explained method of Lagrange multipliers. To find the maximum and minimum values of f of x comma y comma z subject to the constraint g of x comma y z x comma y comma z equal to k, assuming that these extreme values exist and del g not equal to 0 on the surface g of x comma y comma z equal to k. Del means gradient. Okay, next find all values of x comma y comma z, and first step, okay, find all values of x y z and lambda such that the condition del f equal to lambda del g and g of x y z equal to k. The second step is evaluate f at all the points of x y z. The result from step A, all the points we can get from this points x y, this step x comma y comma z. The largest of these values is the maximum of f. The smallest is the minimum value of f. This is the procedure of method of Lagrange multipliers. If we write the vector equation del f equal to lambda del G in terms of components, then the equations in step A become Fx equal to lambda Gx. Next, Fy equal to lambda Gy. Fz equal to lambda Gz. And last equation is G of x, y, z equal to k. This is a system of 4 equations in the 4 unknowns x, y, z and lambda. But it is not necessary to find explicit values of lambda, values for lambda. To find the extreme values of f of x, y subject to the constraint g of x, y equal to k, we look for values of x, y and lambda. This is the two. Now I explain two variable function. For functions of two variables, so to find the extreme values of f of x, y subject to the constraint is g of x, y equal to k. We look for the values of x, y and lambda such that is del f of x, y equal to lambda del g of x, y. Lambda del g of x, y. Okay. And g of x, y equal to k. This amounts to solving these three equations by using these three unknowns fx equal to lambda gx and fy equal to lambda gy and g of x, y equal to k. Okay, these three by using these three equations I got the values x, y and lambda. This is the method of Lagrange multipliers in two variable. This is the three variable. Next, here suppose the subject to the constraint, subject to this constraint is given, then the condition becomes del f equal to lambda del g plus mu del h. Another one constant is added. Okay, del f equal to another one unknown constant. Del f equal to lambda del g plus mu del h. This is the condition. Replacing this condition by this one. This is the two constraints. Suppose you have two subject to the constraint, then you have to use this formula. Okay, this is the definition. Next, I will give one example of finding the extreme values of the function and subject to the constraints also given by using Lagrange multipliers. Okay, Lagrange multipliers method. Find the extreme values of the function f of x, y equal to x square plus 2y square on the circle x square plus y square equal to 1. Here f of x, y is this one and the subject to the constraint is x square plus y square equal to 1. We are asked for the extreme values of f subject to the constraint g of x, y equal to x square plus y square. This is equal to 1. Using Lagrange multipliers method, we solve the equation del f equal to lambda del g and g of x, y equal to 1. Here 1, k is 1, which can be written as fx equal to lambda gx, fy equal to lambda gy and g of x, y equal to 1. What is fx? Here f is here. Fx is 2x equal to lambda into what is gx? This is also 2x. This is first equation. Next, fy, that is 4y. 4y equal to and g lambda into gy. What is gy? This is also 2y. This is second equation. Fourth equation is g of x, y, that is x square plus y square equal to 1. Third equation is third equation. From 1 we have 2 cancel, so x equal to 0 or lambda equal to 1. So 1 gives x equal to 0 or lambda equal to 1. If x equal to 0, then 3 gives y equal to plus or minus 1. Y gives y equal to plus or minus 1. Okay. Next, if lambda equal to 1, first case x equal to 0, next case lambda equal to 1. If lambda equal to 1, then y is equal to 0. From 2, Next, so 3 gives x equal to plus or minus 1. Therefore, f has possible extreme values at the point 0, 1, 0, minus 1, 1, 0 and minus 1, 0. This is the f has extreme values at the point, possible extreme values at the point 0, 1, 0, minus 1, 1, 0, minus 1, 0. Next, evaluating f at all these 4 points, we find that f of 0, 1 equal to 2, f of 0, minus 1 equal to 2. Next, f of 1, 0 equal to 1, f of minus 1, 0 also 1. Therefore, the maximum value of f on the circle x square plus y square is f of 0, plus or minus 1 equal to 2. The maximum value is 2. This is maximum value, and the minimum value is 1. This is minimum value. The maximum value occur at the point 0, plus 1 and 0, minus 1. The minimum value is occur at the points 0, 1, 0 and minus 1, 0. That is 0, plus or minus 1, 0. This is the one example of how to use Lagrange multipliers methods by finding extreme values of the functions of 2 variables and 3 variables, etc. Okay, this is one example. These are the main concepts of maxima and minima of 1 variable and 2 variable functions. If you have any doubt in this concept, then you can ask in the comment section. I will try to clarify your doubts. Thank you. See you in the next video. If you like this video, please like, share and subscribe my channel to encourage me. Thank you.